that, if we want to address the needs of our client countries, we need to put quality now. And it's a generalized need all around the world. And so it is at the center of our breeding scheme. Now, our strategy has been to really identify our best quality material within the simian germplasm, widely adapted, high-yielding, drought-tolerant simian germplasm, and use those in our process. But bringing in blood from different germplasm groups that are known to have good quality parameters, especially for color, for yellow color. That is the trait that has been lacking in the simian germplasm historically. These germplasm pool are obviously Australian, French varieties, some of the Italian varieties, and the desert durum out of California and Arizona. These germplasm groups, even if they have very, very good quality, they have issues of disease resistance. Most of these are stress susceptible. Some of them do not have the same yield potential, the same drought tolerance, or some of them are very late. And so it takes a while to be able to take the genes for good quality from these germplasm groups, put it into high yielding, drought tolerance, simian background. So it has cost us quite a bit to have to use this material, but we have done it successfully. Now, the evaluation scheme. When do we evaluate for quality? Well, we spend a lot of time and resources testing for quality of the parental material we use before making crosses, whether it's our material or material that is introduced. And now we can say that in every cross we make thousands of crosses every year, and in every cross we make, at least one of the two parents has high quality. We do not make crosses bad quality by bad quality anymore, because all you're going to get is bad quality. Okay? We try to put as much quality in the cross combination that we use in the parental lines, and but we don't do any early generation testing. So in the segregating phase, when we have single plant or single family, we do not do any selection for quality. Why? For logistical reasons. We have 2 cycles per year. So when we are harvesting our plots in Obregón in May, we have 2 or 3 weeks to harvest, prepare the seed, send it 2,000 kilometers south, and plant. We do not have the time to run thousands of quality tests before we plant. So basically, that's why we don't do early generation testing. It doesn't mean that it cannot be done. It can be done. Most of the traits, or several of the traits that we use, and we'll talk about it in a minute, are highly inheritable enough, easy enough to measure, that you can do it in segregating phase, from F2 to F4 plants. But we don't do it because we don't have the time to do it. But once we put things in yield trials, and for the entire yield trial phase, for the 3 years, everything is sent to the quality lab, and we are very, very ruthless in terms of what we select and what we discard in terms of quality. The traits that we look at are primarily grain characteristics, gluten strength, the ability of the gluten to make a strong dough, or strong enough to be able to go through the machines in the industry without collapsing and without making problems in the machine, and yellow color. Protein content, mostly secondary and secondary fashion, and I'll explain why. Okay, in terms of the grain characteristics, what we look at is viscousness or non-starchy kernel. Obregón and our testing conditions are not very good environment for that, because they're so good that there's very little of these problems of starchy kernel. But everything that has this problem in the segregating phase is eliminated visually. We look at F4 grain, we look at F2 grain, and everything that does not have acceptable grain is not thrown in the bulk, it is thrown away. The genetic component for the trait is low to moderate, which means that selection, even though we do it, is probably not as efficient as for other traits. And that also, that you can do it, you can solve this problem, the problem of starchy kernel, by management. A variety can have up to 80% starchy kernel, but if you fertilize it right, if you irrigate it right, you can get rid of it. So there is a very important environmental and management component that is probably more effective in taking care of this grain characteristic than genetics. Black point, it is a problem. Again, our conditions are not very good to select for that. The genetic component is moderate, and again, what we do is any black point we have, we see in the segregated phase, we just throw away. Now, in terms of the grain characteristics, the test weight or hectoliter weight, which is an integration of how sound the grain is, it's related to milling yield, semolina yield, so it's very important. And that is something we measure in our most advanced material, but since it takes a little bit of time to really measure it, this is not something we use for our selection. We just measure it, as I said, just in the last phase of our program. Here the genetic component is moderate. There is quite a bit of variability due to growing conditions, but it is important to make sure that the test weight is not low. Kernel size, on the other hand, we really look at it very, very closely, not just from a quality parameter, which is related again to milling yield and semolina yield, but it's also related to drought tolerance. A plant that can develop a big kernel, well-filled kernel under drought, is a plant that is going to be drought tolerant most of the time. So we look at it both for drought tolerance and for quality. And here, the genetic component is moderate to high. The environmental component is very important as well, but here we actually look at it from the beginning of our preliminary yield trials all the way to our multi-environment yield trials. And any line that has really very small kernel or shriveled kernel is discarded. And if you look at the results of the selection, this is material that we have been distributing worldwide in our international nursery, whether it's the yield nursery or the screening nursery, a total of 150 to 200 lines altogether. And this is data of these 150 to 200 lines when evaluated in Obregon during the selection phase, 2 to 4 years yield data. And then if you look at the percentage, and this bars show the percentage of line with medium to large kernels, basically acceptable kernel size. And over the years, most of our line that we have distributed have at least medium to large kernels, so they have acceptable size, and you can see they're always above 90%. So we allow very, very few percentage of line with small kernels, just to make sure that we don't have a handicap in terms of milling yield, and we have been successful in maintaining the kernel size of the outgoing material at pretty high level, at high frequency. Okay, grain protein content. And here I understand and I realize that what I'm going to say is maybe a little bit controversial and not very welcome by some of the industry. To me, grain protein content is not something you can breed for very successfully. I know that there are a few genotypes that will give you always higher protein contents than other under any yield level. But those are exceptions. Svevo, for example, is one variety that's always higher protein than any other variety at a 2 ton per hectare yield level or at the 8 ton per hectare yield level. It is genetically superior in terms of protein content, but it's 1 in 100. And it's something that you can determine only at the later stage of breeding. You cannot select for early on. And if you select for early on in for protein content, you might lose some yield as well because of the negative correlation there is between these two traits. The genetic component is very, very low. The environment component is very, very high. When you have a situation like this, it's a lost battle for breeder, and it's a battle that needs to be fought at the level of crop management, fertilization, and irrigation. My colleagues, agronomists, can take a 10% protein line with right management, go to 13% without much problem. To get that 3% increase genetically, I need to work 20 years with no guarantee of success. Okay? So, why fighting losing battles? We do measure protein content on everything we put in yield trial. We look at it, but we do not eliminate based on protein content. Again, because of the very low genetic influence in this way. So nitrogen management and management options are probably more effective intervention option for protein content than genetics. There is an approach, however, there has been programs that have used genes from Triticum dicocoides, the loci called GPCB1 gene, that does increase protein content overall under various level of yield, independently from yield. And this gene has been tagged with molecular markers that are very, very easily used, that are very effective, and we have developed several lines with the gene using marker-assisted selection. The problem is those lines, yes, they have high protein, but they have about 20 to 30% yield penalty. And so, obviously, we haven't distributed those lines, and we're still working with it, trying to grow big population, trying to break that linkage between high protein and low yield due to this gene. This gene is basically a senescence gene. It tells the plant, shut down everything, and so the protein gets high, but the grain does not fill properly and yield is not achieved. Yield potential is not achieved. So we're trying to break this linkage to see whether we can use with genes, have the high protein without the yield penalty. I have to say that in breadwheat, in places, in dry environments like in Canada and South Africa, they have released variety with this gene that have high protein and are okay for yield. But for us, under the very high yielding conditions that we have not yet been able to use this gene properly. We're working on it. Some other groups worldwide, in Canada, in California, and I know that in Italy, some groups are working on it. And let's see what we can arrive at. But for now, so far, it has not produced acceptable results. Gluten strength is the ability of the gluten, the protein of wheat, to form a complex that is strong enough to go through all the different machines in industrial scale without being too sticky, without being too tenacious, or without being too weak. Okay? As you all know, and I'm just going to mention it very fast, the gluten complex is made of gliadin that are monomeric and gliadin that are polymeric. In durum wheat, unlike in bread wheat, the most important part that gives you strength and elasticity is the gluten complex, the polymeric complex. And within these, only one loci really gives you, has a very significant importance. It's the GLUB3 found in 1DS and the short arm of chromosome 1B that really determines whether a durum line has strong enough or weak gluten. There are other loci that have been identified, but they really have minor effect. Those same loci have major effect in gluten strength and bread wheat. But in durum wheat, really GLUB3 is the most important part. And easily selected for. And so now, again, I'm going to say things that maybe are not well accepted here in Italy, but they are, I think, true from a global breeding standpoint. Gluten strength can be measured by many, many types of instruments. Albergraph, mixograph, extensograph, glutomatic, and so on. You can spend $2 million equipping a quality lab and do some very interesting research, and I'm not saying that these equipment are not useful. They are very useful for research. They may become very useful when you're trying to market on a variety basis, certain for some niche market. But in terms of giving you the information you need to make progress in gluten strength or to maintain a minimum gluten strength, they're probably too much and not as needed. You can measure gluten strength with a very easy test, sedimentation test, using 1 gram of ground wheat and measuring the sediment after you suspend it in SDS and lactic acid. And so this test gives you a parameter that is very highly inherited, very high genetic component, and very low environmental component. So it's ideal for us to test for gluten strength. Okay? So using this, we have been able to maintain at very high level the number of lines that have at least acceptable gluten strength. We're not talking about a very, very strong line only, but from acceptable to very strong. And as you can see, that the great majority of our material that we are distributing in the international nursery don't have any defect in terms of gluten strength. And we've been doing that just with this very easy, very fast, very high throughput test, doing hundreds of sedimentation tests in a day. Okay? Now, the trait we have been having problem with is called the yellow color. Yellow color is due to lutein, which is a pigment that is found in the endosperm of durum wheat. And here there are several loci that have been identified, and all have multiple alleles. We don't know exactly which allele is better than the other. There are some genetic studies that have shown, compared a few alleles, but there's still a lot to look at. And here the genetic component is high as well. And the environmental component is moderate, so we use it very, very heavily. It can be quantified by extracting in butanol, or we can actually look at the yellow color index using a colorimeter. And either methods are good enough, or are high throughput enough, and correlates very well with semolina and pasta coloring. What we do is we use a colorimeter, like most programs around the world. And if you look at here, we started a few years back with quite a bit of line in our material that are not very good for color, about 30%. It has been reduced thanks to our selection in our material. And then it went down again a little bit. And this reason why it went down is because we have to look at other traits. We have to be pragmatic. We've used a lot of material that is stem rust resistant or leaf rust resistant or Septoria resistant that has very low yellow color. And we wanted to distribute new sources of resistance, improved for yield and resistance. And those lines turned out to have low color. We accepted them nevertheless to be able to provide national program with resistance sources, even though they didn't have the right color. But we are working on it, and we are doing very well. So, in conclusion, for the work we do on quality, is that it is a central part of our program, even though we use it with some pragmatism. We do not look at the highest quality material. We don't look at premium quality parameters or levels of parameters, but we make sure that at least acceptable levels are there in our germplasm. But whoever looks for really the highest possible level in color or in gluten strength will find a certain percentage of our material that has it. Okay? And we have done it using very, very quick tests that allow us to keep these levels high enough in our germplasm. So I think my time is up.
Well, we're just going to give you a 5-10 minute break.
Okay. All right. Okay. All right. So as far as I'm concerned, this is the last slide.
Okay.
Yeah. For this session.
Thank you very much.